You see it every single day, right? The sun. But have you ever stopped to think about how it really works? I mean, what's the secret sauce? What's the engine that has kept our world going for billions of years? Let's get into it. 4.6 billion years. Just let that number sink in for a second. That's how old our sun is. It's a timescale that's just, honestly, it's almost impossible for our brains to even process. And for every single one of those years, it's been blasting out this just unbelievable amount of energy. But here's where things get interesting. Back in the 19th century, the smartest people on the planet, using their best science, calculated the sun could only last for maybe 25 million years. And that was a huge problem, a real head-scratcher. Because, geologists had already figured out that the Earth itself was way, way older than that. The numbers just didn't add up. So what was going on? What were we missing? What kind of physics could possibly explain how our star keeps burning for so long? All right, to really get a handle on this mystery, first you have to appreciate the sheer mind-blowing power we're talking about. Okay, look at this number. 3.8 times 10 to the 26th joules per second. That's a 3.8 with 24 zeros after it. It's an amount of energy that, it just completely dwarfs anything we can comprehend on Earth. So how do you make sense of a number like that? Well, try this on for size. It's like 91.6 billion megaton bombs going off every single second, non-stop. And right away, that tells you something. No ordinary fire, not even the awesome power of gravity just squishing the sun, could possibly explain that kind of energy output for billions of years. No way. And there you have it. That's the core of the problem right there. You've got what the 19th century theory said, about 25 million years. And then you've got reality, a star that's billions of years old and still going strong. This wasn't a small error. This was a chasm. Science was missing something huge, something totally new. So the answer, as many of you probably know, turned out to be nuclear fusion. Case closed, right? Well, not exactly. In fact, figuring that out just opened up a whole new can of worms, an even deeper, more baffling puzzle. Okay, stick with me here. The sun is basically a giant ball of hydrogen, which means its core is just swimming with protons. Now, protons all have a positive charge, and what do we know about positive charges? They repel each other vigorously. It's like trying to push the north poles of two super strong magnets together. There's this massive invisible wall, an energy barrier called the Coulomb barrier that's pushing them apart. Now, the sun's core is hot, really hot. We're talking 15.7 million Kelvin. So you'd think, okay, that's got to be enough heat to just smash those protons together to overcome that barrier, right? Nope, not even close. And this is the part that is just so wild. According to the classical physics we all learn in school, the sun is nearly 200 times too cold for fusion to happen. To actually break that barrier head-on, you'd need temperatures in the billions of degrees. So by all logic, the sun shouldn't be on. It shouldn't be shining at all. So what gives? Well, the answer comes from the completely bonkers, wonderful world of quantum mechanics. It's a little thing called quantum tunneling. It's the universe's secret cheat code. Instead of having to get enough energy to climb over that enormous repulsive wall, a proton can just, poof, appear on the other side. It sort of ghosts its way right through a barrier that should be impossible to cross. Now, for any one proton, the odds of this happening are ridiculously small. But the sun has an unimaginable number of protons all trying at once, trillions and trillions of times every second. And with that many chances, it happens just enough. That is the real secret to how the sun works. Okay, so we've got the quantum secret weapon that makes it all possible. Now let's look at the actual recipe, the step-by-step process that's cooking away in the sun's core. This whole process is called the proton-proton chain, and it all starts with step 1. 2 protons manage to tunnel and fuse together. This is the real bottleneck of the whole operation. It is incredibly slow. Why? Because it also involves one of the protons turning into a neutron, which is just a super rare event. Get this, on average, a single proton in the sun's core will wait billions of years before this happens to it. But once it does, bam, the next steps happen in the flash, and you eventually end up with a super stable helium-4 nucleus. And this process, this proton-proton chain, is the absolute main event. It's responsible for like 99% of all the energy our sun pumps out. There's another process, the CNO cycle, that makes up the last 1%, but that's really more of a big deal in stars that are much more massive than our own. And this is where Einstein enters the picture. You see, when you're all done, that final helium nucleus is just a tiny bit lighter, about 0.7% lighter than the 4 protons you started with. So where did that little bit of mass go? It wasn't lost. It was converted directly into pure energy. All the light and heat of the sun. That is E equals mc squared in action, right there. Okay, so this is a beautiful theory, right? It all fits together. But how do you prove it? How do you look inside the core of a star that's 93 million miles away and check your work? Well, the proof came from these tiny, ghostly particles that fly right out of the core. And, of course, they brought their own brand new mystery along for the ride. 60 billion. Right now, as you're listening to this, 60 billion solar neutrinos are passing through your thumbnail every single second. These little guys are made during the fusion reaction, and they don't interact with much of anything, so they just fly straight out of the sun's core at nearly the speed of light. They're like little messengers, telling us exactly what's happening in the sun's engine room, right now. But there was a problem. A big one. When physicists built the first experiments to catch these neutrinos back in the 60s, they only found 1/3 of what the theories said they should. For 30 years, this was known as the solar neutrino problem. It was a crisis. People seriously wondered, did we get the sun completely wrong? But it turns out the model of the sun was perfect. It was our model of neutrinos that was incomplete. We discovered something amazing. Neutrinos can change their identity, their flavor, as they fly through space. Our detectors were only built to see one type. Solving this mystery was a huge deal, a Nobel Prize-winning discovery that, in the end, proved our understanding of the sun was dead-on accurate. So this entire incredible scientific detective story, figuring out how our own star works, it's led us to one of the most ambitious projects humanity has ever attempted, trying to build a star right here on Earth. The thing is, you can't just copy the sun's playbook. The sun has a major advantage, its own colossal gravity, which does all the squeezing for free. Here on Earth, we don't have a star's worth of gravity lying around. So to contain the fuel, we have to build these incredibly powerful magnetic cages. And since our star in a jar isn't nearly as dense as the sun's core, we have to crank up the temperature, way, way up. And just look at this. This is how much hotter we have to go. To get fusion going in a reactor on Earth, we need to reach temperatures over 100 million degrees. That is literally more than 6 times hotter than the core of our own sun. It's kind of nuts when you think about it. And listen, this isn't science fiction anymore. This is happening right now. We're seeing record-breaking results, literally billions of dollars in private money pouring in. And there are serious plans for the first commercial plants. 35 different companies are in a sprint to get pilot plants running in the next decade or so. The competition between countries like China and the US, it is white hot. The race is well and truly on. So think about this journey. It all started with a simple question. How does the sun work? And now that same quest for knowledge has brought us to the very edge of creating our own miniature suns right here on Earth. So the big question for all of us is, after all this time, is humanity's own star finally about to rise?